So we are now at the third hands-on module. In the previous two, we have discussed module number 1, overall pump dimensionality, interchangeability, different types. Second module, we open up the pump. So the gasket separating the wet end of the pump, the casing from the bearing housing. Then, and we discussed impeller. It was open impeller, threaded on the shaft. We now will open the sealing chamber, sometimes called stuffing box, and we'll discuss the differences. And we'll see what's inside. So I loosen the nuts a little bit, and then the first nut is off. So is the second. And now the stuffing box came out. Well, let's pay attention what happens. This is what we just removed. And I'll get a little bit closer in a minute, but first let's see, it exposes the shaft. There's a sleeve on the shaft. If I take this sleeve out, this sleeve is protecting the shaft. The edge of the seal, the inner side of that, this is what goes and locates it on the shaft against the shaft step before the threads. The outer side of the sleeve, this is where the gasket and the sleeve come together. So it looks like this. And this is why we needed that gasket at the impeller to make sure that fluid is not leaking. The water or chemicals doesn't leak from the back of the impeller past this, if the O-ring or gasket was missing, and then it will go under the sleeve and it will leak between the sleeve and the shaft out into the atmosphere. That's the reason for the sleeve. Having the sleeve has pluses and minuses. First of all, if it's a chemical application, that sleeve wears out, or abrasive application, a sleeve wears out or corrodes out or abrades out, it can be replaced. But it makes the shaft smaller in size. The shaft is smaller inside, that means deflections to the shaft will be increased for the same load. On the previous module, hands-on module, we talked about the deflections of the shaft. So a stiffer shaft resists deflections better. That's not to say you can operate a pump at a low flow. But if you do, if it so happens, the stiffer shaft will resist the deflections better. That is called L over D ratio, or L cubed divided by D to the power of 4. And the reason for that fancy formula, L cubed over D to the 4th power, comes from your maybe college class in structural mechanics or structural dynamics, where the coefficient in the module of for the equation for deflections, y equals f L cubed divided by pi 64 pi d to the 4th. So that d L cubed over d to the 4th happens to be a coefficient inside the formula for the deflections. So if L cubed over d to the 4th of a pump is double of the L cubed over d to the 4th to another pump, some competing design, the one that has double that ratio will have half of the deflection. So half deflection, less impact on bearings, on seals, on misalignment, on shafts. So that's a little bit of that's a little comment of the sleeve. On top of the sleeve sits a mechanical seal or the packing. In theoretical module, we look at how packings and mechanical seals look like. But here we mentioned the packings are good for basically non-dangerous liquids, typically water, dirty water, and similar applications. But the packing has to leak in order to lubricate the surface between the packing and the sleeve or and the shaft. And we discussed it in theoretical module, so you can rewind tape to that module and kind of brush up on that. But here we'll just say that because the packing leaks, in order to lubricate what's under it, the sleeve, otherwise it will run dry and burn, that means it has to leak. And if it has to leak, and if it's nasty chemical stuff, or hot oil, or something dangerous, no good. So you cannot use a packing. You can use a packing for many, many applications, and you should. But if it's really dangerous applications like chemicals or hot oil, you have to do something that doesn't readily leak outside, and that would be mechanical seals. Mechanical seals will be single mechanical seal, double mechanical seals, as we cover in this course, time and time again. But here we'll just mention that mechanical seal, single, double, different constructions, balanced seal, unbalanced seal. There's a lot can be said about types of mechanical seals. In this example, we just look on one simplified example for you to get a good feel for that. So let's just see what we have here. So I'm going to take this box. And of course, this part is where impeller was sitting against, remember. The front goes against the casing, the back against the stuffing box or the sealing chamber. They call it stuffing box when it's a packing application. So it's stuffed with packing. They're calling sealing chamber when there's a mechanical seal. Historically, packings came about first, many years ago, perhaps 100 years ago, then mechanical seals, but the name stuck, and mechanical seal chamber or stuffing box sometimes used interchangeably, but I wanted to understand the distinction between packing and mechanical seal chamber or stuffing box for the packing. So here we have essentially a stuffing box or mechanical seal, depending what you put inside of that, and inside of that sits mechanical seal. This portion of this called the sealing chamber itself, and this portion is the sealing gland. Together, they are bolted in this example with 4 nuts. So if we'll remove these nuts with a tool, I'm just loosening the nuts. There's not much to see inside yet. That's why I'm sitting blocking your view slightly, I guess. So now I can remove the gland. Now, what is inside is a mechanical seal. And here it is. So we have a gland. Inside the gland, there's also a stationary face of mechanical seal. Let me take it out. I'm going to show it to you first. And then I try with my fingers kind of push it out. Here. There's an O-ring. I'll have to refer again to a theoretical portion of the module where these pictures are more clearly shown. But that's the stationary. It sits inside the gland. An O-ring makes sure there's no liquid going over it. And the face I'm touching with my hands, which is I really shouldn't, not to put the grease from my hands onto the sealing faces. But because we're only doing now for training, I have no other way of pointing to the seal faces and kind of feeling the smoothness of that. Mechanical seals are manufactured with very, very high degree of accuracy, a couple of angstroms of parallelism of seal faces. They're polished and lapped to a high degree of precision, very sophisticated operation, and that is why when the seal is changed, don't ever attempt to save it. You have to replace it. And that can be sometimes expensive proposition, but unfortunately, there is no other way. You don't have to do it, but then you're taking your own chance. And then On the other side, toward the sealing chamber, sits another stationary face. That will be for double mechanical seal, which we talked in the theoretical portion. But here we have a rotary face, carbon or silicon carbide, and also the metallurgy or materials of the seals. Now this is stationary and this is rotary. Rotary will run against the stationary with a small, very thin fluid film. It better be fluid film. If there's no fluid film, that seal will burn. So you can see from here that the seals can be damaged very easily if they are not running lubricated. So you have to have fluid, which is another lesson. Don't run the pumps dry. The pump runs dry, you don't have liquid supply to mechanical seal faces, they will burn. So they are separated from each other with a very small molecular thickness sliver of fluid, but some fluid is between faces, prevents them from being contacted. If, of course, the shaft of the pump is deflected, as we discussed in the previous modules, deflection of the rotary seal with the shaft will cause it to move like this, misalign against the stationary seal, not a good situation, the seal will leak and gets damaged. That's what causes number one reason for mechanical seals to leak. Excessive loads, either by misalignment or operating the pumps at a flow sufficiently or too far removed from the design point, from the best efficiency point, BAP. Now we see, let me put this down, we see that the rotary carbon, or perhaps silicon carbon that is, in this example, is driven by a couple of pins, and the carrier itself has set screws, set screw here, and the set screws will be attached to, well, you guessed it, to the sleeve. So we have to position the seal somewhere along the sleeve, and where to position it somewhere along the sleeve. That's a challenge on its own. And we can also discuss it a little bit later. But then, once it's positioned on the sleeve, and the pins will engage in the slots of the rotary face, the motion of the sleeve, driven by the shaft underneath of that, impeller, essentially friction of the impeller, that's what drives the sleeve. The sleeve turns, and the seal faces are engaged by the pins, they move against the stationary mechanical seal, and that's what causes the sealing. So fluid cannot now come out from the impeller it cannot leak over the stationary face. Sorry, on this side. The gland, I put it inside the gland, then the seal will run this way. If I assemble now rotary is inside the gland, runs again stationary, and the rest of the seal simply rides against the impeller. The impeller sits somewhere here, and the back side of the impeller here provides a pressure for the mechanical seal area. Now you might ask why the seal has this two sets of springs when only one is needed to push against the side that actually does the sealing. Well, that carrier is designed not for a single seal only, but for double mechanical seal. So if I put a second stationary and rotary faces on this side of the carrier, I'll have now then two sides to seal, one to my left, one to my right. And that we discussed in theoretical module when we talk about operation of double mechanical seal. We talk about buffer fluid, we talk about seal plant flashing, we talk about there. Today, in this module right now, I just want to point out the fundamentals so you can physically see with my hands and your eyes and ears, you can see what happens now inside the pump with the real parts. Okay. So that's a little bit about mechanical seal. Now you saw it in the actual disassembly. So if I would put the seal back together, I would take the gland, and I'll take this is an O-ring. It sits over the stationary seal face. I'll push it in with my fingers, and a proper way of setting the seal is with a fixture that does not push it non-uniformly. You can design a fixture, something like maybe a plastic spool piece that nice and evenly with some kind of separation in between will push the seal gently to make sure that it will position itself properly against the back side of it. There is no gap. And once it's properly positioned, I'm just doing it with my hands. The seal face must be cleaned. Seal manufacturers usually will recommend denatured alcohol to remove any grease and any dirt from my fingers to the seal faces. From then on, the gland is ready to be assembled with a seal chamber. So let's just do that. So we'll take the rest of the seal, we'll put it on the carrier. The carrier then will have to be positioned on the sleeve, and the set screw must be set, but how to actually set it is a science. So we're going to do it at a different time, a different module. But for now, let's say I am tightening with a set screws properly, and it will position on the sleeve. Let me tighten it. Once it's tight, the sleeve can be inserted into the gland. So seal is in the gland. The gland is being assembled. And then with the 4 nuts, okay. Let's go over what we just did. We made a couple of things right, and we did a couple of things wrong. What did we do wrong? For 50 points, who give us an answer? A couple of things. First of all, the sleeve is not set to the carrier of the seal, right? Remember I said it was a set screw, I set it with a tool, but I guess I didn't. So it's running back and forth, so the seal is not set. I have to open it up and set it, but then I have to set it in the right distance. Separate case. Secondly, the nuts are not properly tight. I didn't apply any particular force. And if I did, I have to position it in a cross pattern. 1, 2, 3, 4. I have to tighten 1, 3, 2, 4. 1, 3, 2, 4. Nice and even, so it gets nice compression to the gasket. Between these two parts, there was no gasket. Oops, another mistake. That's a question on your test. What did we forget when we assembled the seal? We forgot to put the gasket. Where's the gasket? There was no gasket when I opened it. So somebody who assembled it before must have made a mistake. So we can do a lot of Sherlock Holmesing fact searching when we're analyzing the failed pump. What happened? It's not necessarily who did it, but what happened so it doesn't happen in the future. So over here we have two injection ports, two holes. 1, 2. These holes are for the seal flush. When we go back to theory, we'll explain more about seal flush and how it operates and how it works. So that basically concludes our basic portion of a hands-on explanation. Couple of things are left to be done. First, to set mechanical seal positioning properly. Set it with a set screw to the sleeve at that position. Insert the gasket between the stuffing box and the sealing chamber. Properly tighten the nuts, and then put the entire assembly back into the pump. But that is now a good start for you to do it. I hope my hands provide you a little bit of a coupled with your eyes and ears to get more understanding, better understanding, rather than just theory of what actually happens inside the pump. So it's almost, I hope, as if you've been inside the pump hands-on, as close as the camera would allow. With that, we're going to conclude this module, and we'll go to the next one. And next will be bearings and lubrication for the pumps.